Hey folks, this lesson is truly intended to talk about slope and rate of change as we get into this next unit. However, I wanted to start with talking about really the foundation of functions again, and kind of wrap up of what we did in Unit 1. And the big idea from Unit 1 is that we have 4 different aspects of a mathematical function, and we use functions to model things in our world. We have all kinds of patterns and relationships in our world, and we can come up with these mathematical models that sort of describe them, or we can use them to interpret or predict, and so on and so forth. Okay, so here's kind of the big 4 aspects. We have some situation, right, and we've been dealing with some of those in class. From that situation, we could create a table of data, and then from that table, if we want, we could graph that data. And then between the table and the graph, we could maybe come up with an equation that models it. Okay, so that's the big idea. And we can start with any and kind of go in between the two. Like if I have an equation, I can build a table. If I have a graph, I could probably build the equation. If I have the graph, I could maybe put some data points on a table, right? All connected, okay? That's the big idea, all right? So given that, let's talk about slope and rate of change, right? So one of the early problems that we did, which I'm sure you'll recall, is this cheeseburger problem, right? We wanted to know how much does it cost for any size cheeseburger at In-N-Out Burger, and we started looking at that 100 case. That's kind of how we were exploring. But at the end of the day, this is what we wanted to find. And could we find any size cheeseburger? And we could, right? And these were kind of our steps. So this is our scenario. We built a table. We started doing some calculations, exploring, and then we found some, like a single, a double, a triple. We found some of the different individual costs for the patty and the cheese, for the bun and the other stuff, and we sort of built a table of data, and then we were graphing that alongside it. Okay, so those two things went together, and then at the end we ended up making a mathematical model, right? So this equation models any size of cheeseburger at In-N-Out, right? And it's connected to the data in the table and the graph, right? So this is our equation where X is the number of patties and Y is the total cost. Okay, so really what we're going to be focusing on today is this part right here. Okay, this part of this model. Okay, and that's our rate of change. Okay, on the graph we call that a slope. Right. So what's our slope? Right, increasing. Right, any kind of increase. All right, what's our slope? What's our average rate of change? And then in our table we could kind of find that too. Right, we can find a rate of change. Right. And these are also all connected. So 90 cents increase. And our table, if we could count by ones, our graph, this would be going up by 90 cents as well. Okay, all connected. Right. So let's do a blank problem to give you another sense of kind of what we're talking about here. Right, here's our scenario. Right, Alex and Gina often run together on the weekends. They usually run a pace of about 9 minutes per mile. I'm just going to underline 9 minutes per mile, okay? And it says their distance varies, but can you find some distances and times they might run? Sure. All right, well, let's start doing this. Let's just say, well, let's start building the table. And we'll say that that miles is maybe our input, and then time could be our output, right? Because the amount of time it takes kind of depends on how many miles they run. So let's say that they don't wake up one morning. They're like, nope, we're not going to run today. They run 0 miles. Well, how long does it take? Well, that doesn't take any time at all. Okay, that's pretty basic, right? What if they only run 1 mile? Well, it says they run 9 minutes per mile. So if it's 1 mile, it must take them 9 minutes. Pretty straightforward. What about 2 miles? Well, that'd be another 9 minutes, right? Okay, so our time would be 18. Well, what about 3? Well, it's another 9 minutes. Right? It's 9 minutes every mile. So 27. Well, what about 4? Another 9 minutes. Well, 5. I'm sure you see where we're going here. Let's see. I'm going to skip though. What if they had a big run? What if they wanted to run 10 miles that day? Well, let's think about that. 9 minutes each mile, or 9 minutes per mile for 10 miles should be 90 minutes, right? So I could include that, right? Totally fine. Now, if I want to plot some of that data, well, let's plot some of that data on this graph, right? Well, 0, 0, definitely. Okay, so again, down here, this is like our miles. And then over here is our time, right? And this would be in minutes. And our miles, yeah, miles. Yeah, don't need a unit for miles because it is a unit, right? Okay, 10 in minutes. 1, 9, so 1 mile, 9 minutes. 2 miles, 18 minutes. 3. So I'm just going to use the same data from my table, obviously. And I'm going to build my graph. That's the big connection between these two. And then 1090, I can't get 1090 on this graph. Not big enough. That's okay. So here's what we're noticing so far, what we should notice. 9 minutes per mile, right? That's the rate. We knew that right away from the scenario. If I look at my table, I can see that is also the case. That's kind of how I built it, right? Based on the scenario. That makes sense. I'm increasing 9 minutes every mile. And my graph is going to show that too. If I look at my rate of change or my slope of the graph, I'm going up 9. So I'm increasing 9 for every 1 mile I run. Right? That happens with each of these. Okay. So if I want to write an equation for this, a model, I'm just going to say my output y, okay, which is my time, is equal to, well, my rate's just 9 times my input x, right? So if my miles were x and my time was y, I just input, let's see, 5. If x is 5, you plug it in. 9 times 5 is just 45. Right? That's my output. So these are the 4 things connected here. Scenario, just built a simple table, threw a graph together from that data, and then I could write an equation to model it. Okay. Big connection, though, is my slope and my rate of change here are all 9. In our equation, it shows up here, whatever is multiplied by the input. In our scenario, obviously, we start with that. Okay? All right. So here's what we want to be able to do. Just straight up is given any one of those items, okay, or one of those aspects, can we find a rate of change or a slope? Yeah, sure we can. All right. We've done this a little bit already. So let's see. I'm going to just do this table here, and it's in function notation. That's cool. Remember, this is like a y or an output. And I'm going to look here, right, and we've been talking about linear, nonlinear. This is definitely linear. It's increasing by 7 every time I can see. Okay. So if it's linear, it has a constant rate of change. We call that the rate of change or the slope. Okay. So what is it? This one's 7. Pretty straightforward. All right, this table, just vertical instead of horizontal. Same idea though. If it's linear, it has a constant rate of change, which we also call the slope. And I want to find out what it is. Well, it looks like this one's decreasing. Let's see, decreasing by 11. Yep, minus another 11, minus another 11. Now, technically, we really should check everything in the table. If it's linear, it should continue forever, so any of the data there should follow that rule. So the slope or the rate of change on this one is just negative 11. All right, this table, let's see. Well, this is pretty basic, right? It's just increasing by 4 every time. All right, but here's the thing, and one thing I didn't point out in the last 2 tables, but now I'll go back and I will. Right? Go back here, my inputs are just, we're going up by 1. Cool, that's really nice. This one, yep, cool, we're going up by 1. This one, we're not, are we? This is actually increasing by 2. The inputs are increasing by 2, okay? So really my rate of change or my slope here is increasing 4, right? So increasing 4 every input increase of 2, okay? So the rate of change here, 4 divided by 2 is just 2. Right? So you can think of that as, let's see, if you snuck a 6 in here for an input, what would that be? Well, that should be 15. Right? If you snuck an 8 in here, what should that be? Well, that should be 19. Okay? So now you can maybe see it a little more clearly. This is actually going up by 2 every time our input goes up by 1. So that's really important. Our slope or our rate of change needs to be per 1 unit. Okay? That's why we often write it this way and then we reduce it down or simplify it down. Okay? All right, so I'm going to look at this one right away. Oh, yeah. All right, so we're going to have to be careful here because this is increasing by 10. Okay, 10 every time. Okay? Let's find this rate of change here. Oh, let's see. This is $2.50. And then, yep, 250, 250, 250. Okay, so I'm good. So I'm increasing $2.50, but that's not my rate because that's every 10 minutes, it looks like here. Okay, so 250 divided by 10 is 0.25. Okay, I'm going to put my dollar sign on there to label it. So this is my rate in this case. If we think about that, this means 25 cents per minute. Okay, so not going from 20 to 30, but if I just went from 20 to 21, let's say, if I could sneak a 21 minutes in there, my charge would then be 17.50 plus 25. So it'd be 17.75. That's the idea there. Okay, again, our slope or rate of change needs to be a unit rate. Okay, all right, so that's on my table. Our graphs, pretty basic, and you maybe remember the idea of rise over run, right? We're always reading our graphs moving forward. Oop, my hand's backward on the on the screen. All right, so left to right, whatever's left to right. I can't tell which way this is going. All right, so I will start anywhere where my line here, my graph is crossing the grid. I'm going to kind of put a point there, and then I'm going to go to my next point where it crosses the grid. Right? I have to move forward. Again, forward, left to right. Okay. Now, to get from here to here, I have to go up 1. So up 1, and then I can move forward 1. Okay. So my slope of this, my rate of change is just 1 over 1, because I just went up 1 and over 1, and that's just 1. So graph is where we really call our rate of change a slope. Okay. All right. Same idea here. Let's see. I'm going to keep red. So I'm going to find a point. It doesn't really matter where you find the point. I usually just try to find it over on the left somewhere because I know I need to move to the right. All right. So here we go. That point, and then nope, 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 nope. Ooh, this is okay. And just for the heck of it, I'm going to go do another one and just make sure that I'm kind of consistent there. Yeah, that looks good. And in fact, if I wanted another one, sure. Right. So I can pick any of these two. I'm going to start at one of them. So I'm just going to start at this one. And I need to move to that one. Right. To move there, I have to first go down. And I went down 2. And then I can run forward. Always run forward. So go up or down, and then run forward. All right. So this is a negative slope because I went down 2. I wrote negative 2, and then I ran forward 3. So this slope is negative 2 over 3. Okay? All right. This one as well, I'm going to find a point. Now, as you do these a little bit more, you'll get comfortable with seeing if the slope is positive or negative just by kind of looking at it. Think of Super Mario running. If you ever play him on Nintendo, he's always kind of facing forward, running left to right. He'd be going downhill here, right? This is a negative slope line. All right, here's another point, and here's another point. Okay, so I can use these two, or I can use those two, or in fact, I could use these two if I wanted to. Let me show you that. Let's do that. Let's go from this point all the way to here, right? Left to right. Okay, so I'm going to go down 8. So I went down 8, and then I ran forward 2. So my slope is negative 8 over 2, which negative 8 divided by 2 is just negative 4. Okay. Now I'll go back here. Well, what if I did these 2 points instead? I'll just kind of sketch that in. Actually, I'm going to erase this. And what if I did those 2 instead? Let's see what happens. If I can find my pen. Here we go. Here to here, I would have to go down 4. But then I only have to run 1. Negative 4 over 1. That's also negative 4. Okay. So it's always going to work. You may just have to simplify your slope down a little bit depending on which points you pick. Okay, but it'll simplify down to the same thing. Okay, and that's constant. Down 4 over 1. It'll continue forever. All right, last one looks a little weird. And after we practice these a little bit, you'll get these really quick too. This, all right, I need to think about moving forward. So I'm going to pick some points. Well, that point works. So does that one, or that one too. Really, any of these. I got a whole bunch of them. And if I think about moving from one to another, so like here to here, I am not going up or down at all. All I'm doing is running, right? I'm just running forward, and it doesn't matter which ones I go to. So this one, since I'm not going up or down at all, my rise is 0. But then I'm just running forward, well, anything, really. Well, let's just say 2. I ran forward 2. Well, 0 over 2 is just 0. Okay. If I ran forward 5, 0 over 5 is just 0 as well. Okay. This horizontal line has a slope of 0. Right? And if you think about Mario walking on this, is he going up or is he going down? Well, neither. It's a 0 slope. He's just going straight. Okay. But that's how you can reason it as well if you want to think of it as rise and run. Horizontal line's just a 0 slope. Okay. All right, equations, right? And we'll practice these up a little bit more too. As we talked about, our general equation for a line is y equals mx plus b. All right, that's kind of how we write our linear models, linear equations. And this value right here, our value that's multiplied by our input, is always our rate of change, or our slope. Okay. So if we have an equation that's in slope-intercept form, finding that slope is as easy as identifying where's my value that's multiplying my input. It's right there. Okay, and I'll use the variable m. M equals 2. That's my slope, or my rate of change. Okay. This one, well, this value right here is multiplying my input. So my slope is 2/5. Okay. So really easy to pick it out of an equation. That's why we call this slope-intercept form, because we can see the slope just straight out. We can also see the intercept, which we're going to talk about later. All right. This one, well, here's my value that's being multiplied by my input. So my slope is just -1/2. And then finally, negative x. So what is this multiplying my input? I can't just have a slope of negatives. It doesn't make sense. What we can do, though, is we can think about, well, negative or opposite of x. This is like it's like -1x, -1 times x. Okay, so my slope here is -1. That one looked a little bit strange, but that's how you have to think about that. Okay, so equations, pick it straight out. It's that m value when it's in that form. Okay. Last thing I'm going to do is talk about a couple scenarios. Okay. So let's see. Arthur woke up and saw that it was 42 degrees outside. 4 hours later, he noticed the temperature was at 56 degrees. Okay. What was the average rate of temperature change that morning? Okay. So we want to know what was the temperature change like over time. That's kind of the rate that this is asking for. Well, let's see. It went from 42 to 56. So I need to figure out what was that increase. Right, well, to find that difference or the increase, I'm going to take 56 minus 42. Right, so it went up, looks like 14 degrees. Right? Okay. 42 to 56, so 14 degrees. But that's not the rate, because it didn't do that in an hour. It did that, it looks like, over the course of 4 hours, so 4 hours later. So this is 14 degrees, but it's over 4 hours. All right, so if I want my rate of change, my average rate of change, it needs to be per unit or per hour. Okay, so I need to think of per hour. So I just need to divide this out, and that's going to give me my rate. So I need, that's not going to, whoop, put it over there. I think that's okay. I want my calculator. Not giving it to me. All right, I got to use my one next to me. You can use your calculator too. My one that is not coming up on the screen. 14 divided by 4, put that on your calculator, we get 3.5. Okay, so 3.5 degrees. I'll put the little degree symbol there. Degrees Fahrenheit. Ugh, science. People who are really picky would probably want me to do that. Okay, there we go. All right, similar kind of problem. Haley's family is draining their pool for the winter. When the pool was full, it contained 11,000 gallons of water. That's a lot of water. After pumping water out for 3 hours, 3,500 gallons still remains. What is the rate that the pump is removing water? Okay, so we do need to know the total of water that's been removed. Right, so let's do that. I need to figure out, it went from 11,000 to 3,500. So 11,000 minus 3,500. Okay, that's going to give me the water that's been removed so far, right? And I think that's 7,500. Okay, you can check my work on that if you want. So that's the amount removed, but that's not the rate because this was over 3 hours, right? This was over 3 hours. So it's 7,500 gallons every 3 hours. Okay, so we need to divide this out or simplify this out. 7,500 divided by 3 is 2,500. Okay, and again, this is a unit rate. We often call it a unit rate, right? So that is, let's see, gallons per hour. Okay. There we go. So that's the rate of change from a scenario. Okay, those are the 4 different ways that we can look at a mathematical model, okay, or a function and find that value that we refer to as the rate of change or the slope. All right, there you go.